All right. Hi all. Welcome to another online causal inference seminar. Today we have Ting from University of Washington talking about Debiased Multivariable Mendelian Randomization. Our discussant today is Neil Davies from UCL. And in the chat, or actually in the Q&A, we have a few people handling questions. So Ting's co-authors, Yinxiang Wu and Hyunseung Kang from University of Wisconsin-Madison are here to answer some of your questions in addition to Ting. All right, today the Q&A session will be handled by Naoki, so I'll let him explain how that works.
Thanks, everyone. So if you have any questions, please submit the questions to Q&A buttons like the below. So if you submit the questions to Q&A, mostly Hyunseung and Yinxiang will be able to answer for your questions. But if the questions are really complex, maybe we're going to stop Ting and Ting might be able to answer your questions. So during the talk, please just submit your questions when things comes to your mind. So without further ado, Ting, thanks for coming.
Feel free to. We see them. Yes.
Thank you. Hi, thank you, everyone. Thank you for inviting me here. And it's a great honor to speak at this online causal inference seminar. Today, my presentation will be about Debiased Multivariable Mendelian Randomization. And this is a joint work with Yinxiang, my student at UW Biostats, and Hyunseung Kang at University of Wisconsin-Madison. And our paper is available on arXiv if you want to learn about more details. So what is Mendelian randomization? Mendelian randomization is a causal inference method. It applies to the use of genetic variation to address causal questions about how modifiable exposures influence different outcomes. And the principles of MR are based on the Mendel's laws of inheritance and instrumental variable method. And more about Mendel's laws of inheritance, and this is so crucial and underlies the premise of MR, is that for Mendelian randomization, it uses this randomness where the alleles that's inherited from parents to offspring is randomly determined. So this random passing of alleles from parents to offspring create a natural experiment that we can leverage. And this is indeed Mendel's laws of inheritance. However, Mendelian randomization is not often done in parent-offspring setting because the data limitation. Data are often not available for parent-offspring design. And even if it's available, it's of smaller size compared to large population GWAS studies. So most MRs are actually in a non-family setting. And studying population share much common ancestry. For example, in UK Biobank, it's European ancestry. And we view the random assignments of alleles as approximate rather than exact. And this is the setting that I will be focusing on in this work. And to talk about the basic idea of Mendelian randomization, I'll use this example of BMI and blood pressure. And to study the causal effect of BMI and blood pressure, it's a very difficult problem because it's hard to measure all possible confounders of BMI and blood pressure. But Mendelian randomization uses this genetic randomness and circumvent the problem of needing to listing all the possible confounders. And it uses the fact that people who inherited certain alleles, they tend to have higher BMI. Like, for example, this genetic variant that's in the FTO gene, it affects calorie intake and affects BMI. So if we stratify on this genetic variant, and this will naturally lead to subgroups of different levels of BMI that's pretty much the same on all other characteristics. And this is due to the random assignments of the genetic variants. And this way we can study the causal effect of BMI on the blood pressure. And in essence, the Mendelian randomization uses the genetic variation to extract some unconfounded variation in BMI and use it to study the causal effect of BMI on outcomes. And if you're a trial emulation person, then it's helpful to think of a hypothetical randomized controlled trial that's emulated by this Mendelian randomization study. And in this case, you can view that as people are randomized to BMI lowering medication. And this leads to some groups with higher BMI, some groups with randomly lower BMI, and we can do causal inference of BMI on outcomes of interest. So statistically speaking, Mendelian randomization uses genetic variance as instrumental variable. It's a commonly used device to deal with unmeasured confounding. So briefly, instrument needs to satisfy these three core assumptions. The first one says that the genetic variant is related with the exposure of interest. And this is easy to justify in MR because we know a lot of genetic variants that are related to traits. And second, it needs to satisfy randomness. And in this figure, it says the genetic variance is independent with unmeasured confounding. And this is true or justified because of Mendel's laws of inheritance. And that's the premise of Mendelian randomization. And the last one, the exclusion restriction, says that the genetic variant cannot have a direct effect on the outcome. So all its effect on the outcome must be exclusively mediated through changing the levels of BMI. And this is perhaps the most disputable assumption because many genetic variants are multifunctional. So they could influence BMI and they could also influence other traits, which may create this direct pathway to the outcome. But for most part of this talk, I'll focus on the setting where we ignore this violation of exclusion restriction problem. So we assume it is correct. And so based on these assumptions, the main idea of using genetic variance as IV to identify the causal effect can be illustrated using this linear structural equation model, where the first one is the exposure model, which says the exposure is related to all these genetic variant ZJs, and unmeasured confounder U and some random error. And outcome is related to exposure, and the causal effect is beta 0, and there are unmeasured confounder and random errors. So basically, we can just plug in equation 1 to equation 2, and this gives us this reduced form, which says that the effect of ZJ on the outcome is beta 0 times little gamma j. And we denote this as capital gamma j. And notice that this leads to a key identification result, which says that the effect of ZJ on the outcome denoted by capital gamma j is indeed proportional to effect of ZJ on the exposure denoted by little gamma j. And the ratio is exactly beta 0. So we can use ZJ to estimate its effect on the outcome and estimate its effect on the exposure. And this helps us to identify the causal effect of exposure on the outcome. So now let's move on to multivariable Mendelian randomization. It's basically Mendelian randomization with multiple exposures. MVMR, it's a helpful extension because it can study multiple exposures simultaneously. Because in some applications, we are interested in how this system of multiple exposures affect the outcome. And in this case, the MVMR will estimate the direct effect of each exposure on the outcome that's not mediated through other exposures. And this is helpful for us to disentangle which of these K exposures is really causal in this system of variables. And there are also a lot of creative applications of MVMR to studying time-varying exposures and interaction effects in mediation analysis. So to illustrate the identification in MVMR, we will also use this linear structural equation. It's having K exposures as denoted here. So here is system equations, and here is the K exposure, each and all of them having like the vector of these K exposures having beta 0 causal effect on the outcome. And we do the same thing, just plug in equation 1 to equation 2, and this leads to having a similar identification result, which says that the ZJ's effect on the outcome satisfy this linear relationship where it's equal to the ZJ's effect on all the exposures and multiplied by this beta 0. And with this identification assumption, how are we going to leverage this to estimate the causal effect? So what is the data that we are going to use? So the setting we consider is the summary data MVMR, and it's basically combined publicly available summary data on gene exposure and gene outcome associations. And this is the most popular setting in Mendelian randomization because it's very, very convenient. You can download the summary data from a lot of large GWAS databases, such as the GWAS, the Open Catalog, etc. And to give an example of how the data look like, here is a very nice application of studying the direct effect of adult BMI and childhood BMI on risk of breast cancer using 270 independent genetic variants. And there are 3 data sets involved. So the first one is the exposure data set 1, which is a GWAS for adult BMI by the Giant and UK Biobank. And from this GWAS, we will do marginal regression of the first exposure on each of the genetic variants. And this gives us the slope estimate as well as the standard error. So these summary statistics are what we will use. And similarly, for the exposure data set 2, we find a GWAS for child BMI. And this also gives us marginal relationships. The marginal effect, gamma J2 hat, and the standard error sigma xJ2. And we find another GWAS for the outcome, which is a GWAS for breast cancer in Breast Cancer Association Consortium. And this gives us similar, the marginal association statistics and the standard error. And in this example, you may notice that actually the data sets that are used for measuring the adult BMI, childhood BMI, and breast cancer, they can be non-overlapping. So it's pretty amazing by using this Mendelian randomization framework that we don't need any individual being measured, both adult BMI, childhood BMI, and breast cancer. They can be measured in totally non-overlapping population. And this creates a lot of convenience because it's hard to measure both the childhood BMI and adult BMI for the same group of people. So for most of this talk, my assumption will be that the exposure data sets are independent of the outcome data sets, meaning that these 2 exposure data sets, they are allowed to have some overlapping sample, but they will be non-overlapping with the outcome data set. And this will be relaxed towards the end of the talk. So now I want to introduce 2 assumptions that we use for MVMR. So it's basically translated from this instrumental variable framework, but all the assumptions will be put on the summary statistics. So the first assumption is the identification assumption in MVMR. And this says that all these marginal association vectors or statistics or variables, like all these statistics, they follow normal distribution where their mean is denoted by this little gamma j's and capital gamma j's. And we assume they are mutually independent with each other. So this is reflected here that this is a block diagonal matrix. So we also assume that the variances are known, although the variances are not exactly known in practice, they are estimated, but this is a reasonable assumption in MR studies when the genetic variance number is much smaller than the sample size. And from the IV framework that we talked about, we will inherit this linear relationship assumption, where the genetic variant on the outcome has this linear relationship with the genetic variant on the exposure. And this is our key in the identification of beta 0. And in our framework, we assume that the number of exposures denoted by K is fixed. So like in the previous example, we have 2 exposures, the adult BMI, childhood BMI, so that's fixed. This is very reasonable in MVMR because currently most of the setting, we are only able to dealing with finite number of exposures or small number of exposures. And we will let the number of IV go to infinity as the sample size goes to infinity, where the sample size is the minimum sample size in all the GWAS data we use. So essentially, this assumption is reasonable when all the IVs are independent, as is the case if they are obtained from LD clumping, and each SNP is very weak, and we have non-overlapping exposure and outcome data sets. And notice that actually all these true values can depend on the N, so they can be drifting sequence. For example, for weak IVs, we have the association statistic, like the association parameter goes to 0 if it's a very weak IV. So we will model it as something that can goes to 0 as the sample size goes to infinity. So this is a weak IV regime. And for common SNPs, meaning that the SNP is common in the population, which means the variance of this SNP is not too small, then we will also have the variance being of order 1 over n. And I'll use this theta to denote its order of 1 over n. And so that's how the sample size come into play in this summary data setting. So basically all these parameters, they can depend on the sample size, but so I'm omitting the n subscript for ease of notation. So the second assumption is really key in our characterization of many weak IVs. So this assumption is a bit technical, so let me walk through this. It says that there exists a K by K matrix, Sn, where the Sn will be used to characterize the convergence rate of this matrix that reflect IV strength for K exposures. So in this construction of the Sn, it's saying that it's equal to some bounded full rank matrix multiplied by a diagonal matrix with this mu1, mu n, square root of mu n1 to the square root of mu nk. And this is reflecting the convergence rate for different direction of the exposure as characterized by Sn tilde. And with that, we will multiply this Sn inverse and Sn inverse transpose on left and right. And this is able to make this matrix being bounded element-wise and full rank. So essentially, the Sn will characterize the convergence rate of this whole IV strength matrix for K exposures. So this is what we propose as a general asymptotic regime of many weak IVs. And this is adapted from this landmark work of Newey and Windmeyer that propose generalized method of moments in weak moment setting. But we adapt their assumption into the summary data multivariable Mendelian randomization. And this is a general regime, and it's more general than a lot of the weak IV asymptotics that are studied previously in the literature. For example, in Stock and Yogo, it's assuming that all the IV strength needs to be of order n to the -1/2. And Sanderson 2021 needs to assume that the IV strength is local to rank reduction of 1. So essentially, one direction is very, very weak. The other directions are similar IV strength. And Chow and Swanson will assume all the exposures converge at the same rate. All the exposures have similar IV strength. But in our framework, we allow for pretty general setting where different linear combinations of the exposure can have different IV strength. And this is important for Mendelian randomization because if two exposures, although they are marginally pretty strong, instrumented by the IVs, if they are very high correlated, then you can imagine their contrast will have very weak IV strength, whereas their individual ones can have stronger IV strength. So again, this is important for MVMR literature, and it's a pretty general asymptotic regime that we will consider in all our theoretical analysis. So this allows IV strength, again, for different linear combinations of exposure to converge at different rates. And this is measured by the mu case. And in classic setting where these IVs, so these association parameters are all fixed, so they are not drifting sequence as sample size goes to infinity, and the matrix is full rank. And if it's a common IV, then the variance inverse will be in order of sample size. And then we can see that actually all the mu k will be equal to n. So this means that all the exposures will of order n. But this is not true for weak IV, where the mu case can be smaller than n. And we will also use the minimum of this mu case to measure the IV strength for the weakest direction. And in case you're wondering, this IV strength matrix has the same rate as the commonly used concentration matrix in IV literature. And also it has the same rate as this other matrix, which we just replaced the variance for the outcome GWAS by the variance in the exposure GWAS. And we will use the latter as the IV strength for the reason that this matrix is scale invariant, because if we scale the exposure somehow, then this matrix is kept the same, whereas this is not scale invariant. And also this matrix is not dependent on outcome, which is more appealing because we don't want the measure of IV strength because it's purely IV exposure relationship. We don't want it to depend on the outcome. So, so that's the assumptions. And before I go to our estimation approach and more results, let me pause here to see if there are questions.
Yeah, so Tin, so there's one question that Boynod asked, is it only applicable for a linear relationship between variables? So I think the question's about the linearity in the model.
Yeah, that's a very good question. For the outcome, we use linear model to motivate. And in the linear setting, the beta zero will be interpreted as the average treatment effect. But the outcome model is not necessarily linear. So actually, in a very fundamental paper of Ting and Zhao in Annals of Statistics, they derive that if the outcome model follows a logistic regression, then beta zero can be interpreted as a conservatively biased parameter for the causal odds ratio. So causal log odds ratio. So that's very nice. And if the outcome is more general, like it's non-parametric, then still the beta zero can be interpreted as a very small change in the exposure, how that leads to change in the outcome. So the outcome model is pretty general. And the exposure model, although I use linear model to motivate, it doesn't assume linear model at all. So it's the same thing as the two-stage least square being robust to the first stage specification. So that's the same here. The exposure model is not required to be linear at all.
Thanks. And I think there's no more questions at this point. So.
Okay, great. Thank you. So I'll move forward to talk about two methods or the inverse variance weighted estimator that's very, very commonly used, maybe the default method that a lot of people use in MR literature. and talk about the theoretical results we derive for these estimators. So the idea of MV-IVW is very simple because of this linear relationship in the true parameter, and also because this holds for all the IVs. Then basically we can just fit a linear model which uses the sample analogs to fit a linear model with no intercept, because this true parameter has no intercept. And then we do this weighting to reflect the fact that different IV may have different measurement error and strength. And this is indeed the same as the MV-IVW that people commonly use, and takes this formula. However, the MV-IVW is usually biased in Mendelian randomization due to the measurement error in this little gamma J hat. And this is the well-known weak IV bias in MR literature. So the really in the MV-IVW method, it's ignoring that this little gamma J hat is measured with error. So, but in practice, because the little gamma J, the true parameter, can be pretty small, so the measurement error is pretty non-ignorable. Like it cannot be ignored compared to the signal level. So this IV strength can a lot of times be quite substantial. Like the weak IV bias can sometimes be quite substantial. And some heuristics of why there is weak IV bias. So we can do this approximation. Essentially, the expectation of the IVW is approximately this expectation inverse times this other expectation. It's not exact, but it gives good heuristics of what's going on. So if we calculate the expectation, then we realize essentially this is a second moment. So it has a signal part and the variance part, whereas the numerator only involves this summation of MJ matrix. And we can see that if the variance part is not small compared to the signal part, then this IVW's mean can be quite far away from the true parameter beta 0. Whereas in strong IV setting, if the VJ is small compared to MJ, then the bias is not so large. So we study theoretically the MV-IVW in our asymptotic regime. And so we basically confirm a lot of the observations that are observed in MVMR studies, and we provide more detailed characterization of IVW's performance. So under our assumptions, when beta 0 is non-zero, and when P goes to infinity as the sample size goes to infinity, so we assume the number of IVs is very large, then the following conclusion holds, that if the minimum IV strength, which is the minimum value in all the mu case that we assume in the weak IV asymptotics, divided by the P squared goes to infinity, then the IVW is consistent and asymptotically normal. And if this divided by P goes to infinity, then IVW is consistent. And if this divided by P converts to a constant or 0, then the IVW will converge to this thing. It's not beta 0, so it can be biased. And when beta 0 is equal to 0, then the IVW is consistent and asymptotic and normal, as long as P goes to infinity. So this is saying that the IVW, because the regime A and B are very hard to obtain in typical MVMR studies. It's requiring IV strength that are unachievable in a lot of MR studies. So this explains why in practice, we can often observe weak IV strength in MR studies. And so weak IV bias in MVMR studies, sorry. And also we noticed that if we are testing the null hypothesis that all the exposures have 0 effect on the outcome, then IVW is pretty robust. And this agrees with the univariable IVW's result. And in regime C, the IVW can be biased either away or towards 0. So this is pretty concerning because in univariable MR, IVW is biased towards null, which is more conservative and perhaps less concerning. But in this case, because it's a vector that's multiplied by beta 0, so this means some components of beta 0 might be biased away, some may biased towards 0. So in summary, the weak IV issue in MR literature is a well-known problem. But from these results, from this analysis, we found that the MVMR is more vulnerable to weak IVs than univariable MR for the following 3 reasons. First, weak IVs can occur when SNPs are weakly associated with some exposure conditioning on the other exposures. And this is like much more common than univariable setting. Like univariable setting, we just need to find SNPs that are strongly associated with each exposure marginally. And in the case of like adult BMI and childhood BMI, it's very possible that their genetic correlation is very, very high. And this means that the SNPs effect on the 2 exposures are highly correlated and they can be weakly associated with one conditioning on the other. And using the second reason is using simple p-value cutoff is insufficient because it only gives marginal relationships. And lastly, the weak IV bias can either toward or away from the null. So we propose this Debiased IVW estimator. It's a very simple modification, just minus this variance matrix in this inverse part. It's not so surprising, perhaps, because with this modification, we can do the similar exercise, and then we see that this makes sure that the DIVW estimator can be well centered at beta 0. So from this simple modification, we see that the MV-dIVW is robust when IVs are moderately weak. And this is a multivariable extension of univariable DIVW in our prior work. This is not too surprising, but when we evaluate this estimator in simulation studies, we realize this estimator can be quite unstable in setting where the IV strength is very weak. This is because we need to calculate this matrix inverse, and it can be unstable when the matrix is close to. And so to improve it in finite sample, we propose this other estimator called MV-adIVW, so this adjusted DIVW, and to stabilize the matrix inversion. So if we denote this matrix inversion by S inverse, then we basically replace S by S plus phi times S inverse. And in this way, this effectively turns every eigenvalue of S, which is denoted by this lambda j, to this quantity. So it augments every eigenvalue by certain quantity that's away from 0. And this makes sure that the eigenvalue of this stabilized matrix inverse can be bounded away from this value. So it effectively addresses the singular issue. And it's also very nice because when this direction is very strong, in the sense that the mu j is large, then this adjustment will be pretty small because it's inversely related to mu j. Whereas if the mu j is very small, then the adjustment will be moderate as controlled by the phi in order to make sure that this direction it can be well addressed. So with these 2 estimators, the DIVW and the adIVW, we show the following theorem, which says if the minimum IV strength denoted by mu minimum divided by square root p goes to infinity, and if our choice of the tuning parameter phi in this matrix inverse adjustment is satisfy this rate condition, then both estimators are consistent and asymptotically normal. They're asymptotically equivalent because phi equals 0 also satisfy this condition, but the adIVW has better finite sample performance. And also notice that this rate condition is much easier to satisfy compared to IVW, because IVW required that this divided by P goes to infinity. So this is much easier to satisfy in MR studies. And you may wonder, how do we select the tuning parameter phi? Because it needs to satisfy the rate condition that we require. So essentially, we choose phi to minimize the following objective function. And it's basically like a residual sum of square in a weighted version. And we let phi to be chosen from this interval. And this interval is chosen for the reason that we noticed that if this simple version of the mu, which is the minimum eigenvalue of the estimated IV strength matrix, divided by square root P, if it's larger than 30, then the vanilla DIVW already perform very well. So we make sure that this interval is very, very small so that we don't do any adjustment, basically. And whereas if this is very far away from 30, then we allow this interval to be larger, so there is a larger range of tuning parameter to choose from. But essentially, we choose phi to minimize this objective function. And we have two extensions. The first one is extending to balanced horizontal pleiotropy. Although the multivariable Mendelian randomization is already dealing with horizontal pleiotropy in some sense, because it's allowing to adjust some known pleiotropy pathway in a MVMR framework. But still, there are some, it's unsure that whether there exists additional horizontal pleiotropy. So in the sense that this may be a direct, additional direct effect of the IV on the outcome. So we model that as adding this direct effect, and this direct effect is a random effect, and it's independent with IV strength. And we can show that both our MV-dIVW and MV-adIVW are still consistent and asymptotic normal, but the variance is larger because of the random effect. And then we extend to overlap samples between exposure and outcome data sets. And this is also important because in some cases, if the outcome data sets, including like a UK biobank, it may include some samples in the exposure data set, then there is correlation between them. Then we model this as having this correlation matrix. And this leads to additional bias because of the correlation. So, but we can easily adjust it. So we just minus this correlation matrix in the numerator part, and then this can have a good performance. And this same adjustment can be applied to the adIVW. And sigma, this correlation matrix can be estimated using non-significant steps. So more details are in the paper. So here I wanted to show some quick simulations to demonstrate the performance. It's a setting with 3 exposures, and their causal effects are denoted in the top row. And we have in total 145 SNPs. And we, in this setting, the minimum IV strength divided by square root P is 7.4. And in this case, the IVW agar median, they are all biased. And for these 2 exposures, they are biased towards 0, but in the 3rd exposure, they are biased away from 0. And they all have poor coverage probability due to this weak IV bias. And MRBE is another method that's also have large bias and very unstable in this weak IV setting. And GRAPPO performs well, except slight under coverage in this setting. And DIVW has some bias as indicated. So this is slightly away from -0.5, also for the others. And the standard deviation is pretty large, but this can be effectively improved by the adIVW. So adIVW can have small bias and good coverage probability and small standard deviation. And finally, I want to just quickly talk about our application. This is an application of lipid subfraction on the CAD, and we want to study the causal effect of individual HDL subfractions on coronary artery disease that are independent of traditional lipids. And here, the data we include these 5 data sets, where this is the traditional lipid data set we use as selection, this we use as exposure data set, and subfraction data we use as selection or exposure, and this is the outcome data that we will use. And using the selection data set, we select 273 uncorrelated SNPs using p-value cutoff 10 to -4. And using the exposure and outcome data sets, we subset these SNPs and then conduct MVMR analysis using each of the subfraction and adjusting for all the 3 traditional lipids. And this is the results we obtain. So we have considered 6 subfractions, and their IV strength are here. So we consider like all the methods we evaluate in simulations. And essentially what we see is that the IVW agar median, their point estimators are all closer to null, likely indicating weak IV bias, because from what we know theoretically and in simulations. And ADIVW is very similar to grapple in most of the settings. And so also for this subfraction, the ADIVW actually has the narrowest confidence interval compared to the others. And the results from ADIVW suggested that these 3 subfraction, they have protective effect against the CAD, while these others may increase CAD risk. So in summary, in this work, we study MVMR. And so, but in this talk, we start with the MR that leverages genetic variation to address causal questions, and it emulates a randomized controlled trial and provides a triangulation across multiple sources of evidence for causal inference. And MVMR is our focus. It's an extension of MR to multiple exposures. And in this work, we propose a general asymptotic regime for many weak IVs. It allows for linear combinations of exposures have different degrees of IV strength, and it's a feature that hasn't been studied in MVMR before. And we established the asymptotics of MV-IVW and theoretically show its weak IV bias. And we propose 2 estimators, dIVW and adIVW. And adIVW has a nice adjustment that effectively improves dIVW and can reduce the weak IV bias. And this is extended to balanced horizontal pleiotropy and overlap sample situations. And that's all I want to say. Thank you so much for listening.
Thanks, Ting. Very nice talk. Okay, so your collaborators are working hard to answer all the questions. But if you'd like, I can read out this one that's left, since we have like a minute. Okay, this is a long question. So it says, in traditional mediation analysis, it is not obvious how to handle causally correlated mediators. Since MR is like a mediation analysis where direct effect is required to be 0, I was wondering whether it might be problematic too if the multiple exposures are causally correlated. For example, cardiometabolic factors. Maybe you address these potential causal correlation in between exposures in the initial slides, as the talk had already started when I connected. So.
Yes, that's a very good question. So let me share this deck again. Like in this deck, we do allow causal correlation among the exposures, and this is not an issue in MR because with these SNPs. So we use an IV analysis in this case, and so and in this case, it doesn't need to, so it accommodates causal correlated exposures with no problem.
Great, thank you so much. Okay, so we move on to our discussant now. Neil, please feel free to share your slides.
Thanks, and thanks so much for inviting me today. It's a real pleasure to read this paper and to be able to discuss it. I'm going to limit my comments to, I guess, the bigger picture implications of what Ting's just presented. There's, as I'm sure many of you are aware, been a huge increase in the number of Mendelian randomization papers. So the ease at which we can conduct Mendelian randomization studies today, especially with two-sample methods and large databases, has resulted in a very, very rapid increase in the number of publications and papers. And these are principally all applied papers. There'll be a small number of methodological papers here, but here this is just in Google Scholar, combining MVMR with Mendelian randomization. And since the method was proposed about 10 years ago, there's been roughly a doubling every year of people using these approaches. Now, that's quite a lot of scientific output in a huge range of journals using these approaches. Almost all of them will be using the methods that Ting just described that really don't deal well with weak instrument bias. And as a conflict of interest, I'm going to have to include a number of my papers that have been published using this exact technique, which I think quite probably have spurious standard errors as well. Now, I wanted to start just by focusing on the benefits and the kind of promise of MVMR, why it was developed and why it can be useful. So it's got a huge history as instrumental variable analysis. The entirety of econometrics was when it was developed originally, the estimators allowed for multiple exposures. So it's not a huge extension of very widely used econometric techniques. Equally, weak instrument bias is very well understood, both in the statistics literature and in the econometrics literature. But interestingly, weak instrument bias has been largely focused on situations where there's a single instrument, and there's been relatively little assessment as here about the implications of weak instrument bias in the context of multiple exposures. And it's really important to emphasize here that it's multivariable Mendelian randomization is not less prone to bias from pleiotropy. It's simply allowing you to control for one pathway. So there's nothing, all of the other pathways which could bias your analysis, they're still of concern in MVMR analyses. Now, the biggest limitation of MVMR is clearly pleiotropy, and we can use it to model at least one additional exposure on top of the exposure of interest. However, typically what happens in applied studies is that researchers are interested in much, much larger data sets and far greater numbers of exposures. And in those situations, weak instrument bias for multiple exposures very quickly overwhelms and uses up all of the information in your data. So if you've got more than a handful of exposures, as you might do if you've got a large proteomics data set or metabolomics data set, it's going to be very, very difficult to come up with plausible and precise estimates using these techniques. And we've kind of seen these in some of the attempts to use these approaches on very, very wide data sets with a very large number of exposures. And what is emphasized in this paper is that we need to demonstrate that not only are our instruments associated with our exposure of interest unconditionally, they're also associated conditionally. And that's been identified a little bit. The Sanderson paper cited in Ting's work gives a test statistic for evaluating this and reporting when you're likely to suffer from weak instrument bias. But crucially, this doesn't allow you to entirely overcome it. Now, the cost, as was highlighted in the simulations, is really in terms of power and precision. So the estimates that you get from the bias-corrected approaches, they're less precise. And so this leads to an obvious question about, well, does this mean that this is an estimator? A little bit like some estimators that have been proposed in the past. So MR-EGA is the most widely used example of an estimator which has some appealing theoretical properties, but is potentially underpowered and imprecise. And so in motivating the use of these methods, perhaps it'd be better to change the framing of the paper and actually reduce or be slightly more blunt about the implications of both the method and the theory that you're developing here. That actually the thousands, well, the 9,000 papers that we might expect to be published using these techniques this year, a very large fraction of them may well be spurious in terms of the precision that they're reporting and the findings that and the inferences that they're attempting to draw. And I don't know if that's something that you've considered, because it's kind of a bit of a almost a downstream what's the word, problem for applied scientists. But there are quite big implications given the scale of use of these methods, which your results suggest are quite probably flawed. So I'll be very curious about your view on what should applied researchers be doing, and what should we do with all of these papers that have used these methods that may well be wrong. And then a final challenge is just about IV2. Like a lot of the MR literature, this is the independence assumption, like a lot of the IV literature, we kind of assume that this assumption holds, that genetic variants don't have any confounders, and what's true within a family also holds across the population. But there's quite a lot of evidence, recent evidence, that IV2 is not as universal as we might like. What's the implication of some of the sources of bias that we have discussed in the literature for approaches like MVMR? So population structure, indirect effects, and assortment are the three that we've thought about most. But I'd be very interested in your take on that. So yeah, other comments other than I really enjoyed reading the paper and thought it was great was Tim Morris's guide to evaluating simulation studies and reporting them, and also just including the code for the simulation. It might have been there, I might have missed it, but it would be really cool for people to kind of dig into the details of the data generation process and how you've kind of assessed all these different estimators. But yeah, my view is it's really important contribution to the literature, a really important problem. And yeah, if you've got any ideas about how we improve the quality of the MR papers that are being published and work out how big an issue this is for applied researchers, and I'd be very, very curious. So I'll leave it at that and hand over to the chair.
Thank you, Neil. Great, thanks for the discussion. Ting, we have still 5 minutes. If you'd like to respond, also if your co-authors would like to discuss this further, feel free.
Yeah, thank you so much, Neil, for the very nice discussion. I can try to answer some of the questions, or not answer, but discuss some of the comments first. Like the first is about bias and precision. And yes, so DIVW is when the IVs are strong, as you mentioned, if all the exposures are strongly instrumented conditioning on the others, then IVW and DIVW are very similar. So the adjustment is basically negligible, and they are very similar. So in the case where the IV is weak, so the IVW has biased, so and has poor coverage probability, whereas DIVW, although the standard deviation is larger, but it's asymptotically unbiased and with good coverage probability. So I think, yeah, so I think that addresses the bias and precision question. And the second is that, yeah, so I agree, like MV-IVW can sometimes be suspiciously precise. And so I think it's important in application to report F statistic. Like in our case, it's a IV strength quantification. If we are interested in all the exposure effect, then we require the minimum strength to be strong enough so we can report that statistic. And also, if it's a univariable analysis, then I would say, although it's IVW is biased, but it's valid for testing the null hypothesis. So I can still interpret that confidence in whether that confidence interval covers 0 or not, although the magnitude is not interpretable for univariable IVW. But for multivariable IVW, that's not the case. I think it's very problematic because it's only valid for testing all the traits have 0 causal effect, which is not of interest in many cases. Like oftentimes we adjust for traits that we already know is affecting the outcome. So, I think, yeah, so my take is we shouldn't use the IVW blindly. We should report F statistic and also use other methods that are more robust to weak IVs. And lastly, I think there's a question about IV2 assumption, and I totally agree. It's too simple to say that it's hold because of Mendel's laws of inheritance, because there's so many confounding going on in the genetic outcome confounding that's going on by population stratification and other things. And this can sometimes alleviate it a little bit because of the so when people adjust for like some principal components and other things when obtaining the genetic effects, but that's but some residual confounding can still exist, and this create correlated pleiotropy, which is the hardest type of pleiotropy. And so I felt this needs more work, where there's some very nice approach in univariable MR, like the clustering approach to identify additional pathways, etc. So this can have the potential to be extended to MVMR. That's all. I welcome any other input.
Thanks, Ting. Yeah, Neil, if you'd like to add something, or one of co-authors, feel free.
I guess that the only thing I would add is, are you being too polite, both in the paper and the way that you're presenting this, in that the implications of your method, your results in your simulations, are really very, very serious for a very large number of papers that are being published in a very large number of high-profile journals. And if you are correct, and if we could demonstrate how wrong the standard errors are for these MV-MR papers, that would actually be quite an important result for the literature that people and editors need to know about, that you need to correctly model your MVMR analyses and allow for and overcome this weak instrument bias. I don't know if maybe I'm being too blunt there, but it just seems like a bit of quite a potentially big problem that you've identified.
Totally agree.
Okay, great. So then we will wrap up. Thank you all for the comments and the nice discussion. Hope we've given everyone something to think about. All right. Yeah, so once again, thank you to Ting and Neil, and of course to Hyunseung and Yinxiang for answering all the questions in the Q&A. Next week, we'll have a talk by Eva Diaz from New York University, so hope you all join us for that one. Have a great rest of your week, everyone.